All right. Hi. Thanks everyone for coming to the second September 2022 edition of the Distributed Systems Reading Group. I am going to immediately hand it over to Philip, who's going to run this session and possibly many coming up as well. So first off, he knows this paper pretty well. He's given presentations about it, et cetera, before, and also has agreed to take over the reading group going forward. Just my schedule's gotten pretty wild, and I'm running low on time. So he's very graciously agreed to help run this, as well as Brian, who's unable to make it today. And so with that very short intro, Philip, please take it away.
All right. Thanks, Brooke. Yeah, so hey, everyone. I'm excited for this paper. It is efficient set reconciliation without prior context. And let me just drop you the link in the chat. One sec. Oh, yeah. OK, perfect. Thanks, Quinn. Thanks, Quinn. Does anyone want to do a summary of this paper?
I've got it if no one else wants to. Looks like it's me then.
Good. Go ahead.
I figured I'd give someone else a chance because I've already done one. Oh, yep.
Should I do a screen share? Does it make sense? I think so.
Yeah.
I'll go ahead.
Seems reasonable.
There we go. Go ahead.
Right. So, like Philip said, this is set reconciliation without prior context, or specifically, it's set difference, which you can use for reconciliation. So they provide in this paper an algorithm for figuring out set difference between two nodes with only one round trip between them. And the algorithm that they describe is particularly good for syncing small differences, even if the set is large. So if you have like 1 million elements and you've added 10 since last time you synced up, this algorithm is great for that. So the sort of key main component of this algorithm is invertible Bloom filters. It's the whole deal with this algorithm. So Bloom filters are a data structure where you take all of your elements and you hash them such that you can put them in multiple cells. So you hash them like once or twice or thrice. And every time they go to a cell, you increment the count on that cell. And you can tell if something is in your Bloom filter by taking that thing and doing the same hash process. And if all of the cells that it would have hashed to have a non-zero counter, it's in your Bloom filter. Invertible Bloom filters, as the name implies, are Bloom filters where you can extract some data about the elements that were in them or inserted into them, which you can't do with normal Bloom filters because you only have the count of elements for each cell. So invertible Bloom filters add a ID sum field, which is just the accumulated XOR of all of the elements that get added to each cell, which means that you can potentially unxor those elements out and get an element out of the cell if there was only one added to it, or you could cancel out all the others. I think this is specific to this paper. They also add a hash sum field to their invertible Bloom filters, which is the same as the ID sum field, but instead of just XORing the element, you XOR the hash of the element into it. And this is used for dealing with false positives later on. And finally, now that we know what an invertible Bloom filter is, the big thing that this paper provides, the sort of key insight or the key construction component, is they define subtraction for IBFs, which is actually very simple. You subtract the counts and you XOR the different sum fields, the ID sum and the hash sum, so that if you have, like this diagram shows, if you have cells that have the same element, they'll cancel out. So the main idea of the algorithm is you compute the invertible Bloom filter for the set on each node, and then you subtract them and find all of the cells that only have one element. And you can extract that element's value from the ID sum because all of the other values that got XORed into it got canceled out. So you can see in the third and fourth cells on the diagram, the W and Y values just totally got canceled out, and you can extract the v and the z values. And so the idea is that since you can extract these values and you know what other cells they go to, you can also subtract that element out from all of the other cells it would have hashed to, and potentially get more cells that only have one element in them, and you can rinse and repeat. And hopefully, assuming you've tuned your Bloom filter correctly, you can extract the whole set difference this way, because all of the similar elements will have canceled out, hopefully. So the algorithm is dependent on the number of cells in the filter and the number of cells each value hashes to. If you don't have enough cells in your filter, you just don't get to extract the whole set difference because there's too many collisions. And if you have too many cells, it's not too big a deal. You've mostly just wasted space and time. Similarly, with the hash or the hash locations, you can tune it so that like each element gets hashed to 2 cells or 3 or 4 or whatever. And if you have too few hash locations, you are very likely to find cells that only have a single element. But the problem is that they won't be subtracted out from very many other cells. So you won't necessarily have a good chance of extracting the whole set difference as a result. And conversely, if you have too many hash locations, you're going to have a lot of collisions, and you might not even have a cell with a single element that you can start subtracting stuff out from. So this algorithm is dependent on the size of the difference, because that's what determines how many cells you need in order to make sure that you have not too many collisions. So they then provide the second piece of their algorithm, which is a set difference estimator to figure out how big the difference of the sets probably is. So their set difference estimator also uses IBF, which is good at set difference stuff, as we've noticed. So their set difference estimator algorithm looks something like they split the universe of potential values of the sets into increasingly halved partitions. So you have like all of the even values and then all of the quarterable values and so on. And then they compute an IBF, an invertible Bloom filter, for each of those partitions. They suggest using the trailing zeros in the binary representation of the elements that you're inserting, because that's a nice way, that's a very convenient way to partition the universe if you've got like 32-bit values or whatever. But they also point out that you may need to hash things if your values, your elements are not evenly distributed across the set of all 32-bit values or whatever. And you can solve that by just hashing stuff. So the way the estimator is used is a node computes all of these different strata of invertible Bloom filters and then transmits them to its partner. And what the partner does is, starting from the smallest partition, the smallest partition, and moving to increasingly larger partitions, it counts up how many elements it was able to extract from the difference. So it's doing the set difference thing, but on the smaller and increasingly larger partitions, until it finds a partition that it's just unable to extract the full set difference from. And it takes the count of all of the elements it was able to extract, and it multiplies them by 2 to the power of the index of the last set difference it was able to extract values from. And this gives us an estimated size. So the final algorithm looks like node A sends the strata estimator to node B. Node B can use that to figure out how big the set difference probably is. And then it can send a calibrated IBF, the correct number of cells for the estimated difference size, to that first node. And then that first node can calculate the difference. And we're done. We have a set difference. Finally, they go through characterization of their algorithm. So they implemented a daemon that uses their algorithm on Linux in C. And they used it to answer 4 questions. So the 4 questions were, what are the optimal parameters for the IBF. So how many cells do you probably want, and how many locations should each element hash to? Because those are things you can tweak, and you want to tweak them so that they're good and not bad. The other questions are, how do you tune the strata estimator so that it's sufficiently accurate and doesn't give you too much overhead in its estimate? And then finally, they compare their difference digest algorithm and IBFs generally to other algorithms and look at what it's best for. So the answers to the questions are relatively straightforward. The optimal parameters, you want a hash count of 3 or 4, depending on whether your difference is greater than 30 elements or greater or less than 30 elements. For strata tuning, the rule of thumb is you just multiply the number it spits out by about 2. It's the specific number they came out with was 1.4 times, but rule of thumb is 2. For the other algorithms they compared to, it was some of the algorithms were better when the differences were much larger, but they also happen to be more expensive computationally. Whereas their difference digest and IBF were great for small differences, like I mentioned at the beginning, even if the set size was large. So if you have 1 million elements and there's only been 10 new ones added, that's fine, that's cool, that's perfect for this algorithm. Whereas other algorithms were better in other cases. In particular, when you were computationally bound, it was good for deltas smaller than 2%. And for when you were bandwidth constrained, it was good for deltas smaller than 14%, at least compared to, they compared it to the naive, you transmit the list case. And finally, in order to get the best out of using this particular algorithm, it is best if you are doing live updating, online updating pre-computation of the Bloom filters rather than computing them on demand. There are cases where it might make sense to compute them on demand. I think they point out that in the bandwidth constrained case, it was useful potentially to compute them on demand, but usually it made more sense to be updating your strata estimator at the very least as new elements were added and removed from the set, so that you could just send it over immediately. And that's everything, I think.
All right, thank you for that. That was a really good summary. But I know it's also a lot. So does anyone have questions around something to clarify or something regarding how the protocol works? Something we should go into more?
So I have, so in strata estimator, so when they the algorithm 4 that they have specified, insert S into ith IBF, the last step. Is it similar to what they are doing for IBF, like k hash function and storing it? And how do they count the number of elements in the difference? Do they use the same approach, slight modification of the IBF decode method to count the number of elements? These questions, because it would depend upon how you insert in ith IBF the elements.
So
is this,
for estimating,
yeah, go ahead, sir. Pardon me. Yeah.
no worries. So for estimating the difference size, they are using the count of the number of elements they were able to extract from the different smaller strata partitions that they made. So they make a bunch of small IBFs over increasingly smaller partitions, and then starting from the smallest partition and getting bigger, they figure out how many elements they can extract, and that's so they're computing the set difference for all of the elements with the highest bit set to 0, and then all of the elements with the second highest bit set to 0, and so on until they find one that they can't extract from, and they multiply by a factor of a power of 2 based on how far they get. So that's how they estimate the difference. It's not based on the final IBF, but on the fancy estimator thing. Although I'm not exactly sure mathematically why their estimator works, just that they say that it does.
I think your second question there, if I understood you correctly, was how to get the total size of the set. And I don't think they mentioned this in the paper, but just intuitively, I imagine that would be taking the absolute difference of the cardinalities of both IBFs and then adding the size of the difference to that. And I think that would give you the size of the total set.
Or
I see Philip thinking, so I'm happy to have that fact checked.
No, that seems correct. But is the idea of like estimating the size of the whole set before or after reconciliation? Because after reconciliation, you should have the whole set. So technically, you can count it. But I'm trying to think of like points in time during the protocol in which you already know the set size.
So I when I read it, I felt that when they are dividing IBF into from 0 to ith 2 to the power L, log of 2 to the power L, log L, they are like still when they are inserting, they're using different K hash set to insert it, similar to what they are doing in the IBF implementation when you're inserting an element. And when they are counting the number of elements, the difference upon the set, they're not directly taking the cardinality difference for ith and for both the nodes, for both the sets on different nodes. They are following something similar to the process that they used for when they were decoding the IBF, like counting the pure elements, first taking the pure elements and then taking the difference, and then counting all the numbers of elements.
Yeah, if I'm understanding correctly, that sounds like what Philip was just saying about how you can run through the protocol and then count the result you end up with.
So count the pure elements and then subtract. So this is what he meant.
Okay.
So pure elements are the one where your difference would be 1 or -1.
Mm-hmm.
And so then you subtract out the pure elements once you detect it. So then again, you're counting those pure elements, then new pure elements that then you subtract it out till all the differences become 0.
Yeah,
because he didn't explain this part, how you're counting the number of elements in the paper.
Oh, okay. I think so. This is your question is regarding the what happens during strata estimation, right?
Yes, when you're counting, like, let me be specific. So in the algorithm 5, the last line, and it's the right hand side, the number of elements, how you're counting that.
Yeah. Yeah. I
FM,
guess
FM doesn't help there. It's I think.
What do you mean by FM?
FM is the Flageolet and Martin paper they mention in 3.2 on the left there.
Ah. Okay. Yeah, I guess like the number of elements in the set difference is literally decoding the set difference there and just counting how much you could decode in case you could decode. Yeah.
So I think it's something that might help you. I'm not quite sure where your misunderstanding is, or your but the one of the things that I think makes it make more sense is that because you start at the tiniest partition and work up to increasingly larger partitions, the set differences are going to be like very small to begin with and growing larger as a result. So the first element, you just do the same sort of set difference decoding just on this very small partition, and you get a small difference. And then you just take the cardinality of that difference and add it to your counter. And because it's small, it's not going to be an issue. Like, you're definitely going to be able to decode some of these into a set difference, even if it's not the full set difference. And then you just throw away the values of the elements, at least the way they're doing it here. So the values of the elements don't matter. You're just decoding increasingly larger set differences on different partitions of the set. And then using their cardinality, how many elements are in them, to figure out the counter. I think that's it.
Yeah, specifically maybe to that point, the reason that we expect that at least one of these sets in the estimator, in the strata estimator, decodes, or one set difference is here this line. All of these, so the I strata in the strata estimator only contains a small number of elements, because it's very unlikely to have with a uniformly distributed universe, let's say hashes, to have a hash with like lots of zeros in it. And so you're comparing two IDFs that encode very little amounts of elements. And so when you subtract them, it's very likely that they can decode. And you just continue on. You start with the strata that is most likely to or has the least elements, and you continue until you cannot decode anymore.
So let me put it in simpler words. So what is being discussed is that in algorithm 4, when you insert an element S into ith IBF, it's just the count that you're inserting, right? Like if you have seen, if the ith has seen 3 elements, like S1, S2, S3, that maps to ith IBF. How it maps, like I understand that part, but suppose it maps to the ith IBF, S1, S2, S3. So how would you store it in this ith IBF? Is it that simple count is being stored? Is it being hashed? Then in the similar to what IBF stores for like calculating the set difference the same way, or is it a single hash that is being used to store? And if it's, I'm clear how if it's multiple hash that are being used to store, similar to what it was done in 3.1, I understand how the difference would be calculated. Like this value difference is calculated. But after you have calculated the difference, how do you calculate the number of elements?
Okay, I think I understand where the mismatch is between both of our understandings. And my impression of the paper is that in algorithm 4 there, when they insert into the IBF, that is running through essentially algorithm 1, if you go up one page. And the difference being that here on that first line of algorithm 1, instead of being SI being the elements of S, this would actually be the elements of the IBF for that IBF, or sorry, the elements of that IBF. So it's going to run through that entire encoding algorithm.
Yes.
And do
yes.
the ID sum, the sum, and the count.
Yeah, this is what I was trying to say, that it would run this algorithm 1 to store that value. Then when you calculate the difference, they would be like pure functions. You need to count pure elements and then subtract it. So it would be similar to algorithm 3 that they have defined.
Yeah,
Yeah,
I think
exactly.
it's using algorithm 3 to count the elements in the difference. Yes,
and that is also happening per stratum. They just haven't introduced the stratas at this point, so it's not in the pseudocode.
Also, I saw Marc-Antoine raise his hand, so please go ahead.
Yeah, I want to make sure the other conversations close, because this is a new question.
Okay. I see. So has this clarified the question?
Yeah. So this is what I was like. I agree with the explanation. I also think that this is how it's being done.
Yeah. All right. Cool.
I'm a bit curious about a practical matter. So if I understand well, it's convenient to keep the IBF at different strata so that you can just send it on request when you have a size estimate. My question is, how many layers do we want to maintain? Because there's no theoretical limit on the size of the IBFs that you want to maintain. And so there should be a practical limit. I don't know if that's approach. I missed that in the paper. I don't know if anybody has an idea about that.
So I think it's going to be, you're going to have you take the universe of the elements that you're inserting into the IBF. So if you imagine it's like 32-bit words, you take the cardinality of that universe, so 2 to the 32 minus 1, and then the log of that gives you the number of strata.
Okay.
And then
Oh, it's per 32 bits basically, so 32 layers, 32 strata.
Log 30, or yeah, sorry, yeah, 32 strata. That's my understanding of the paper.
That makes perfect
But everything
sense.
has to be based on the size of the elements you're putting into the IDF and the like number of possible elements.
Could we,
On-
yeah, I guess we could choose to only take a different step function, right? Take the strata 1, 4, or 1, 3, 7, and so on, right? Or 0, 4, 12.
Do you mean like merging subsequent stratas so that you're...
I'm saying instead of keeping all the strata for all bit counts, you could just take every 4 bits, have a step, and then, okay, I don't have this one, but I have this one above to reduce. I'm thinking if we use, for example, SHE 256, do we want to keep 256 strata?
On page 9, just under figure 9, they mention they provide a specific amount that you might want for calculating the strata. So they say it's log base 2 of the size of the delta that you're targeting. So they target 10 strata because that's log base 2 of 2000.
Okay.
And then because they're doing hybrid estimator stuff, they can drop 3 of those strata and use those bytes for the minwise stuff. But
to clarify what
is,
you just said, does that mean that it's not based on the size of the universe and they just always do 10? Am I misunderstanding something there?
I am not entirely sure. They just say from figure 9, we see that the strata estimator performs better for deltas under 2000. Thus, we would like to keep at most floor of log base 2 of 2000 equals 10
see.
strata.
It's bound on the number of strata.
Yeah.
I think in this case, it is actually, if you have a big difference, you will have lots of strata where the decode will succeed, or maybe I don't know. I think this seems to be like somewhat like a cutoff point for the hybrid strata that they're trying to think of.
I wonder if the message here isn't, okay, above 2000, use another algorithm because other algorithms behave better.
Oh yeah, Philip just pointed out that this is about the hybrid estimator specifically here, where they're doing the minwise sketches alongside their strata estimator. So that 10 strata bound probably doesn't apply to the just pure strata estimator.
Yeah, I have something to bring up here in this paper, which I think is interesting to discuss, and maybe also kind of related to what Marc-Antoine said. And that is, what do you think are like good use cases for this possibly, and which ones are bad ones? I know I've heard some jokes about, yeah, the evaluation kind of ruins the paper a little bit at the end. So I'm interested in hearing what your thoughts are.
The evaluation ruins the paper? I'm not sure I understand that part.
I don't know about ruins, but it was definitely, the evaluation is mostly just we wrote an implementation and tested it, and here are some facts, which was less compelling, at least to me, than like here is this really neat idea with invertible Bloom filters, which was like felt mind expanding, especially since they were doing Zor magic. To answer Philip's question, it seems like it's best for, I mean, the general answer is small deltas, but that's boring. Like cases where you're regularly syncing back up, so you're syncing your albums to your media server from your phone, or vice versa, or whatever, where it's only going to be like you added 20 new tracks and then that gets synced. As opposed to, I think in one of the examples they say peer-to-peer, they use like BitTorrent as an example, and that seems, all of their examples are like, when you're finishing up a torrent and you've only got 3 new blocks, like, yeah, it totally makes sense in that case. But there's also the case where like you're just starting a torrent and you have no new blocks. That seems like not a great case for this. So it seems like sometimes you may want to do like partially apply this, like Marc-Antoine said, where like if your delta is big, just use a different algorithm.
Yeah. It's
I'm
like
curious
sort,
if
right?
Oh, sorry, go ahead.
No, it's just like sort, like below 3, just use a bloody bubble sort, and above that, start using the fancier sort algorithms. Go on.
Well, I was going to say, is the strata estimator useful? Like, I mean, it helps you figure out what the set difference is. So you can apply that generally. And if you get back that you're like, oh, it's like a large order of magnitude, you know, like this is, so, you know, we're off by like 50% or something like that, then you just fall back to another algorithm. And if it comes back and it says like, we're really close, then you use this algorithm, right?
Yeah,
always
absolutely.
default to scan, right? But
Yeah.
no, I agree. I mean, that's the kind of issues I see as well. And to me, the ones that I saw obviously are like that. Like I think the sorting example is a good example of where they kind of falls. Also, like, you know, dealing with that kind of the dynamic. You know, obviously they say it like I think a couple of times. You have to really understand that. Yeah, you have to understand what your cardinality and what your diff sizes are going to be beforehand. Which, you know, a lot of systems. Long-lived live running systems, it seems like untenable. They do talk about like the ability to learn from the client over time or something like this. So maybe that's how you know when to switch. But again, and then they also then in their implementation for key-diff, they like, you know, they use everything static in terms of the predetermined sizes for the invertible Bloom filters, and that's, you know, I think it's a very academic paper variance of an implementation, which, you know, again, one of those really hard things that work in practice, because keeping all those sizes then constrains having all this extra space that you may not need depending on that situation as well. That's one that kind of came to me as well.
But I think in a lot of real life situations, you're also dealing with the need for continuous sync between, think CRDT, right? We each have a big event set and we're each creating a few events at a time and sharing the new events. In that case, it's obviously perfectly adapted, right? It's just, there are use cases where it's beautiful. Now, of course, events also have the time constraint, anything new since, but again, if you're resyncing after a while, it's like, okay, what is, if it's a distributed, let's share events in a CRDT pool, it's brilliant.
One of the subtle limitations, not with what you were just saying, Marc-Antoine, but just in general, is that it only makes sense to use if there's some expectation that the other side of the protocol isn't going to have the entire set. One of the things I was thinking of when I read this paper was an application we had almost a decade ago when I was doing malware analysis, where we would collect malware samples in the wild with basically like a custom like BitTorrent protocol that would pull blobs of malware off of different honeypots we had in the wild. But because those honeypots would only ever have the entire malware sample, an algorithm like this wouldn't actually be helpful, because we could always just ask for whatever we were missing instead of trying to do that set reconciliation first. And I think you would see a similar problem for a lot of the like BitTorrent and file transfer examples they're talking about, where you often are working with seeds that have the entire file that's being transferred, rather than like a heterogeneous set of peers that each have like non-overlapping blocks.
Yeah, this is why I was naming CRDT, where everybody is a source, but you're absolutely right. It may be much simpler if one of the peers is supposed to be complete.
I think the CRDT example is a good one because there, every peer can add to their own set. And so without some amount of communication, there's not really a great way of knowing what that difference is.
Yep.
Yeah, I was gonna say, as you brought that up, Quinn, like, this probabilistic case, obviously, if you're really offline for a long time and your set difference, a lot of heterogeneity, as you mentioned, then the performance bottlenecks that come with this in terms of what they seem would actually be really bad if you've been offline for a long time and you're like, cool, let's sync, and then, oh no, we don't gain the benefits of it. So that's interesting.
I really liked the example they gave about dealing with ad hoc networks, like in like emergency and rescue situations, because I know that is one area that like local first software seems like a really promising application of, because any sort of latency in an emergency environment or like network relying on network connectivity, self-service, etc., can actually cost lives. So anything you can do to keep things as local as possible and synchronizing with as little energy usage as possible is a huge win in any of those applications.
By the way, I think I mentioned it last week, but when I was reading that up, I was rooting around that general space and found another article, which is another approach to the same problem. Just put it in the chat, which they claim is more efficient. So I just want you to be aware that this is not the final word on this problem space.
Cool.
Oh yeah, no, I was looking at this paper, right? This is the PBS paper, right?
Yeah.
That's feeling. Yeah. Actually, I was just looking at this like in the midst of reading that one, and I was like, oh, that's a kind of further interesting take on the situation, right? 2020.
Yeah. Interestingly, they give as a first example of applications is a cloud storage system like Dropbox. Now, again, if people have different computers, everybody can add. Like when people have multiple machines, you can add on each machine. But also distributed database. But there, one database may have all the set, but maybe not if we want to distribute the inserts. Again, it's a good use case.
There was.
Sorry, go ahead.
This is also a sort of general answer rather than a like specific use case, but the fact that it is single round trip seems very useful for. It sounds too cool for what it is, but for like dead drop style stuff, where like I think Fission does a bunch of this in the sort of stuff they're doing, where you publish something to like a public file store of some sort. In Fission's case, IPFS, and so you can just like publish your strata estimator, and then everyone can compute a set difference from that, and you don't need to be online for that at all. You just need to publish the estimator, and you're good. That's it. That's the whole thing.
Is that? I'm a bit confused by the single round trip aspect, by the way, and I didn't read deeply enough maybe, but it seems to me you give the strata estimator and then you give this strata and then that strata and then that strata, and there's a cutoff. So isn't there a non-single round trip aspect to that phase?
I think that's mitigated by you just compute all of the strata. You've decided on 10 or 7 or 8 or whatever at once.
Yeah.
And then you just send over all of those strata. And then the other host, now knowing the size of the set difference, just sends you the full computed IBF. And now you can compute the set difference. One thing I did notice though, and I'm
true.
Pretty sure this is the case, both hosts do not get to see the full set difference. Only the initiator in the protocol that they described, only the person sending the strata out and receiving the. Okay, so maybe it doesn't quite work for dead drop exactly as I described.
It's true that two-way, it's probably optimal to let one host receive the difference, because then that reduces the difference of the next step. So you do want. Is that so?
Yeah. So the first host after the second host has like computed the size of the difference and sent that full like correctly sized IBF to the first host, the initiator, because they've sized their partner has sized the full IBF correctly, the initiator has the full set difference. That's
but what I'm saying
doing the strata estimation. And then if they want both hosts to have the set difference, you can just, now that you know the set difference, you can just send that over. I think it's probably the right move there in an interactive environment, at least.
I think you're still onto something with the dropping the thing, because what I'm thinking of is, imagine a service that just publishes their strata estimator, as well as maybe a bunch of endpoints for different sizes of IBFs that they have. And so anyone can connect to this, and it has this kind of interesting many-to-one kind of topology, where anyone can just compute the set difference without the that central thing having to compute anything per peer or whatever that's connecting to them. They just publish their strata estimator and IBF, and yeah, anyone connecting to them computes the tries to estimate the set difference using a strata, and then fetches the correct IBF, and then knows the difference.
I even thought for a second, let's just push the IBF on IPFS, but I realized IBF will change fairly often, actually. So you don't want to clog a distributed system with that.
So maybe, but there is I think there is something to that idea for these like long offline cases where you maybe have intermittent connectivity, because you can gain network connectivity, compute your strata estimator, put that in some well-known location on like an IPFS node or under like some DNS name or something. And then you can go back offline, continue doing a bunch of work. And then next time you gain network access, there may be like a new difference set there for you to pull down and synchronize, so that whenever you gain network access like that, you're able to synchronize to whatever the last state was without needing to wait for this protocol to take place, especially if maybe the other peers aren't online at all times. Almost having like a synchronization bus that you can like push synchronization requests to be resolved asynchronously.
And I just realized we were talking a lot about the BitTorrent case where there is immovable full set. Then in that case, it makes perfect sense to publish the various strata and make those permanent.
It's like
sorry, go ahead.
A full checkpoint situation, but you've got a really efficient way of so the storage might not be super efficient if you're publishing a bunch of different IBFs, but the like bandwidth and possibly computation is a lot more efficient, because you can just download the smallest IBF that you need. You don't need to download the one that's got way more cells and is thus much larger. Like just it's more bytes because there's more cells.
And just for a concrete,
if you know that your difference is small, you can download the IBF that crams more stuff into the same number of cells, because you know that most of those are going to be canceled out because you already have most of those elements. Sorry, go ahead.
So I was just going to offer a concrete use of the asynchronous use case we were just discussing. Like, there's like a really old like 1950s Soviet movie I'm trying to acquire, and there's one seed who's never online at the same time as me, and I'm missing a couple of blocks. If we could figure out that difference and like asynchronously transfer those to each other so that we didn't have to be online at the same time, I could finally get this old Soviet movie.
That's amazing.
Now I want to know what movie this is.
That is a beautiful example, Quinn. Thank you. And it does, so I think it maybe makes sense for like peer-to-peer cases where like there isn't a single source of truth. So there aren't seeds, either because there just aren't, nobody has the whole thing. Everyone's got like 80%, different 80% of it or whatever, or there literally can't be in the case of like potentially with the like diverging CRDT stuff that Fission has been playing with, where there is no like one, this is the true reality situation. And so it makes sense that you could be just sort of constantly updating small pieces over time.
So we've decided it's good for a fixed reference point, a fixed reference set. It's good for continuous synchronization of multiple moving reference sets. And maybe the least useful case is continuously moving single reference set. Oh, Quinn, we don't hear you right now.
Oh, sorry, I was talking to myself. I was saying your examples in my head to map them to the conversation.
Yes.
I think one thing I want to mention or point out is I think we haven't discussed much the without prior context aspect. Like continuous synchronization, for example, is something where one could argue, well, just remembering the state at which your peer was may be easier than having to compute an IDF. So yeah. I'm still excited by IDFs for the no prior context reasons, though.
Well, I'm trying to make sure I see what the remembering previous state. As I said, in many CRDTs where events have timestamps, like, okay, what's the last timestamp of that I know from this peer? Just give me more recent things. That's a really easy case. But I'm trying to think, what are the cases where we have constantly changing and no timestamps? Many state-based databases forget about where a given row comes from or when it was last modified, in which case, yeah, you do need to look at the difference. But that's a really poor design in the first place. But I'm thinking, are there useful cases where we don't have timestamps? Thinking.
It's a good question, right? Also, I was thinking, if you have this kind of 3-node layout where 2 nodes know about their relative kind of communication, and the other set of 2 nodes also knows when they last synced, but then these 2 nodes have never spoken to each other, even though they have a common other node that they regularly talk to. Can you sync easily between those? I'm guessing you can still do that with timestamps. I'm not 100% sure though.
Well, if you assume that they all have everything that came from the common node, yes. If you don't, that gets interesting. One thing I've been thinking about a lot in my use cases is, suppose that the whole data set is too big. You don't want it all. You want a subpart. You want a query on the data set. And you somehow don't have access to the source, the big data set source, but you have access to a peer who's made a slightly different query. So now you're interested in the query intersection, and then the algorithm makes sense.
Yeah, right. That reminds me of something else. Something that's really cool about these IBFs is that they're very kind of algebraic. You can take 2 IBFs and just sum them. You can take 2 and just construct the difference. And so that allows you to do things like keep an IBF that represents the elements that you're not intending to sync from some certain set. Yeah, Brooke, you have your hand up.
So let's say we take 2 of them and we sum them together, and that includes a bunch of XOR operations. What happens to the common elements?
Oh, yeah, you need to know that those are 2 sets that are, I'm missing the word here.
Like disjoints. Yeah.
That's true.
So no, they're not fully algebraic in that sense.
For once, Zora's magic does not help. Sadness.
What you can do if you wanted to distribute this algorithm across like a cluster of peers is partition the universe with like a hash function to figure out which peer is responsible for elements within a given set. And then you just need to deal with the fact, I guess, that some elements may only appear on some nodes. So I guess it's not so simple, but.
What I find fascinating here, actually, it's quite amusing, is that we have this great algorithm for set difference, which is not directly useful for set intersection. And we can do a kind of approximate set intersection with two Bloom filters in the first place, but it's precisely approximate. So we could construct take out the intersection if we had a perfect intersection, but I'm not sure we do. Or actually, I'm quite sure we don't.
Zishan, you have your hand up.
Yeah, I actually really like that you mentioned the kind of algebraic, concept that kind of comes in here, because in the paper that was linked, the VLDB one, I was looking at that a little bit today. That's taking the error correction codes approach, and they actually talk about why would you use IPVF versus ECC. So I think it's kind of interesting because it definitely feels much more. It's a very different paper when you start taking on like these bit sketch, essentially bitmap sketches that they use. But one interesting thing they mentioned, actually, this is really early in the paper, and they're in the new paper, and I just was kind of wondering, because it says when it critiques the IPVF based technique, and they reference this paper, they say on one hand, IPVF based techniques incur communication overhead that is several times the theoretical minimum d log of like the universe, but have a linear a linear time for coding computational complexity. So it's interesting because in this paper they say that they bring down the communication overhead, and I kind of was, obviously I haven't read this paper in completeness yet, but like kind of interesting that that's kind of one of the things they're tackling. So it's kind of going back a little bit. We were talking about the communication overhead. So I don't know what that 6 times they mean refers to, but just something kind of interesting there.
It's definitely a paper I need to check out. The one that's
sure. But I agree with you on the algebraic thing. I really want to call that out as being, that's something that really kind of comes through in this paper versus something in this error correction code kind of research, which is a lot of.
All right, we have 5 more minutes. Anyone want to contribute something, some last thoughts on the paper?
Yeah, so it's a really minor thing, but do you mind going to the bottom of page 4?
Bottom of page 4. I don't even. Okay.
Over by algorithm 1.
Here?
Yeah. So in that paragraph above algorithm 1, this is a really minor thing, but I just want to point it out as a risk to be aware of for anyone implementing this or similar data structures. But they mentioned that to choose which blocks you fill after computing the hash functions, you should take the modulus by n. And I'm not positive, but I'm pretty sure that as laid out in this paper, there's actually a risk of some bias being introduced by that, because they're not constraining the number of cells in the Bloom filter to be a power of 2. So you can end up in situations where there might be more ways to end up in some cell than others, which in this case may not be a security issue, but in many other applications of algorithms and data structures like this can leak enough information to be dangerous. And the way you usually want to deal with that here is to restrict things to be powers of 2 so that things are uniformly distributed. Or as Philip pointed out last night in the conversation to me, you can use techniques like rejection sampling to filter out any results that fall within that unbiased range. But yeah, Philip, I don't know if you agree that there might be a possible problem here, but they don't call it out. So I just wanted to point that risk out.
Yeah, I think so. And I mean, I guess technically, maybe you could argue they're saying take the modulus by n until indices have been generated. Well, no, actually, never mind. N is not necessarily a power of 2. So I don't know. Yeah, I think it's something to be aware of. Also, when I was implementing this, k distinct indices is also something to be aware of, something you easily miss. So if you happen to generate the same index twice, which isn't too bad if you have a normal Bloom filter, in this case, you don't want that to happen. I don't know how bad it is, but yeah, technically what then happens is you have XOR magic and you accidentally,
Sorry.
wipe out your element. Yeah.
Yeah, if
It
you had
seems
an
really-
even parity, you would wipe it out, and if you had an odd one, it'd be okay, I think.
Yeah.
It does seem like it's probably a big issue though, because hash count is like 3 or 4, at least empirically. And so if you happen to generate the same cell twice and you're picking 3 of them, you have just reduced your hash count from 3 to 1 by accident, at least as far as the Zoring is concerned.
Yes. Also, if you, let's say your hash count is 3 and 2 of them accidentally are the same index, you will never uncover more pure cells by removing this one pure cell. It
Yeah,
kind of
you'll have
needs
like
to be one of the last n cells.
Exactly, because you'll have like a ghost element, because it'll have a count, but it won't have anything in the Zor, or it'll be considered, the value will be considered 0 instead of the actual value, or something like that will happen.
Yeah, right. All right.
Yeah, you can recover it.
We're just at the end of it. Thank you very much, everyone, for contributing. I love the discussion, and thanks for coming. So yeah, that's it. I think we can stop the recording.